Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Students, let us take one more numerical on circular motion. The question is that there is an inclined path which ends into a circular loop. Now the question is that circular loop like this, it goes and goes like that. Now the question is that a body is released, a ball is released from here from a certain height, and I'll just write the question so that it will just complete the circular motion, vertical path. From what height you release that it completes the path. Suppose at this height it completes the path. If I release it from here, it will not negotiate this path. It will fall short of reaching this point. Once it reaches this point, it will complete. It might, if I release from here, it might go up to this part. So when it goes up to this part only, with that energy, it will not be able to complete the vertical circular motion. So basically, what I want is the height, exact height h from where it is released without friction. We are not going to consider friction. This is the radius r given, the height is h, the object is having mass m. Now the question I'm writing is that a ball is released from height h along the slope and move along a circular track of radius r without falling vertically downward. Without falling vertically downward. Not falling downward. So what is that question then? You have to show that height must be 5 by 2r. You have to prove this. That means if I release from a height which must be equal to this, condition must satisfy for the body to move successfully. Basically the question is to find the minimum height when it negotiates the loop. So the question is about the height. This height should be minimum, because if it moves, if I release from this height and it negotiates, then if I release from the greater height, then also it will negotiate. So which height we are interested in? The minimum height. Now the answer to this question is that the solution to this question, we know that for the body to, when it enters a circular loop at the lowest point of the path of radius, suppose r, the lowest point, this is the lowest point, this is the highest point that we have discussed so far. At the lowest point, the velocity is VL, and for the object to move successfully in a vertical loop, the velocity at the lowest point must be under root of 5gr. That means the loss of this, because it is released from here, the energy is purely potential in nature. This potential energy becomes 0 here. That means the loss in potential energy must get converted into the kinetic energy. So, or otherwise I can say that this point is suppose 1 and this point is suppose 2, then at 1 and at point 2 I just equate the energy, the total energy. I'll equate total energy at 1 position and at 2 position must equal, because we have neglected the section. At position 1, the total energy is kinetic energy at 1 plus potential energy at 1. Here kinetic energy at 2 plus potential energy at 2. Now what is kinetic energy at 1? The kinetic energy here is 0 because it is released, because the object is released. At release, when you release, it is 0. The potential energy is mgh, h is the height, must be equal to kinetic energy at this point must be equal to half mvl square plus potential is 0, because this is the reference line. This line is 0 line, this line is h line. So mgh, this m and this m will cancel, and gh equals to, what I'm getting is g and h is equal to half vl the square. But we know that for a loop of radius r, the velocity at the lowest point must be equal to 105 gr. So this velocity must be 5 gr root n square. Then we have got this one, that is 5 by 2 gr. So this gh must be equal to 5 by 2 gr, and from here this g will cancel out, and h equals to 5 by 2 r. And this r is capital R, I've taken, no problem with that. So h is equal to 5 by 2 r. This is what we are supposed to prove, and this is proved. We are supposed to show that the height must be 5 by 2 r, and we got that height must be 5 by 2 r. Okay, thank you.